In this video, we're going to learn how to name ionic compounds. So remember that ionic compounds are those that are made up of a metal and a nonmetal. For example, sodium chloride has a metal in it, the sodium, and a nonmetal, the chloride ion. So because there's a metal and a nonmetal, we would call this an ionic compound. What I want you to get is that the compound has different properties from the two elements that it's made from, or from the elements that it's made from. So for example, if you tried to eat sodium, that would blow your teeth out. It's super reactive with moisture, it would react violently in your mouth, and then basically you'd be severely injured. Chlorine gas, that'll kill you if you breathe it in, but when the two react, when sodium and chlorine react together, it makes NaCl. That's table salt, something delicious that you put on your fries, so it doesn't really kill you. So the point I'm trying to make here is that individually these had basically toxic properties for humans. You wouldn't want to eat sodium alone. You wouldn't want to eat chlorine alone. But once it reacts to form this new compound, it has different properties. So when you're reading about sodium content in your food, you're not really reading about the sodium neutral atom content. You're actually reading about sodium chloride. It's just a shorthand way of saying sodium content. In today's video, we're going to focus on naming binary ionic compounds. Binary ionic compounds, as you can probably guess from the word, means an ionic compound made up of two different elements, binary meaning two. So in the previous slide, we saw the example of NaCl. There's only two elements there. We might have MgCl2. There's two different elements here. There's magnesium and there's chlorine. Okay, I know there's two chloride ions, but it's two different elements, a magnesium and the chloride ion, two different elements. So that's what a binary ionic compound is. We have a metal and we have our nonmetal. So we're going to learn how to name them first, and then afterwards we're going to learn how to write the formulas for these binary ionic compounds if we are given their name. In the next few videos, after that, we're going to continue with some special cases. Some will contain multivalent elements, and we'll see what those are in the next video. So for now, we're just focusing on concepts A and B. Binary ionic compounds, so an ionic compound made up of a metal and a nonmetal, only two different elements present. So let's start off with our naming. Here are the general steps for naming binary ionic compounds. Your first step is going to be to name the metal ion first. So let's say we wanted to name KBr. You have to find your metal ion. The metal is the one on the left. So by convention, metal is on the left, so potassium, and nonmetal is on the right, the bromine over here. So the element on the left of the compound is going to be your metal, and that's the ion you're going to name first. So in this case, we have the potassium ion, and the name of metal ions, remember, doesn't change. It's still just potassium. So K plus is simply potassium. The next step is to name the nonmetal ion, so that's the one on the right. Remember that when nonmetals form ions, you have to change their name. The ending, the INE ending, has to become an IDE ending. So bromine, the ion becomes bromide. And now you simply put the two names together. So KBr is potassium. Bromide. Not potassium bromine, but potassium bromide. Because in the ionic compound, it's really the ions that are connected together, not the neutral atoms. The neutral atoms wouldn't attract each other. So when you think about it, you have a K plus, which is positive, and a Br minus, which is negative, and you know that opposites attract. So the plus and the minus are attracted to each other, and that's really what's holding the ions in the ionic bond, in the ionic compound together. So we'll try one more example. Let's try CaF2. So your first step would be to name the metal. So we have, I'm just going to put our first step here, calcium. Our second step is going to be to name the nonmetal. So we have fluorine, but remember that because it's in an ionic compound, we have to change the ending. So right now I'm just going to write fluorine. Just to illustrate that, I'm going to change this INE ending to fluoride. So now I can put the two names together. So CaF2 is calcium. Fluoride. Just as a little note, some ions are sometimes a bit more difficult to predict their name. So for example, it's pretty easy. For chlorine, it becomes chloride. For iodine, it becomes iodide. But for things like nitrogen, there's no INE ending. So I'm going to point those tricky ones out. Nitrogen, when it becomes an ion, becomes nitride. You should remember this. When phosphorus becomes an ion, also 3- because it's in group 15, easier to gain 3 than to lose 5, it becomes phosphide. When oxygen becomes an ion, it becomes oxide. When hydrogen becomes an ion, it becomes hydride. And when sulfur becomes an ion, it becomes sulfide. So I shouldn't see things like oxygenide, I should see oxide. I shouldn't see nitrogenide, I should see nitride. So these are important for you to remember when you're naming binary ionic compounds. If there are others that seem odd to you and you're not sure how to change the ending, you can easily look them up and add them to your little list of weird name changes. Here there are some practice problems for you to do. So you have to name the compounds. You can do it step by step first, and then eventually you'll be able to do it all at once. So you start off by naming the metal ion. So for example, here you'd put aluminum. Then over here you'd put the name of the nonmetal ion. So we have fluorine, but we know it becomes fluoride. And then you put the two names together over here. I'm just going to write it down here because it's a little bit, there's not enough space up there for me. So aluminum. Fluoride. Now we're going to quickly analyze the formula of an ionic compound because we're going to try to take a name and convert it into a formula. So the formula basically tells you which ions are present. For example, over here we can see that we have the aluminum ion and the oxide ion. And so these little numbers over here, these are called subscripts, sub meaning below or smaller. They're smaller than the letters you see here. They tell you how many of those ions you would have. So for example, I have 2 aluminum ions for every 3 oxide ions. If there's no number written down, so for example, as we saw in NaCl, there was no number written next to them, that's an implied 1. There's actually a 1 here and a 1 here, but we don't have to write down that 1, kind of like we saw with the pluses, so you could just leave it as NaCl. So again, we have our metal, we have our nonmetal, and this is a binary ionic compound because there are 2 elements in it only. And we would name it, just as we saw previously, aluminum, not oxygenide, but oxide, aluminum oxide. So here we're given the name of an ionic compound, magnesium chloride. And what we're going to do is we're going to try to figure out what the formula is using a method called the crisscross method. On the next slide, I'm going to show you how to do a different method called the charge balancing method, which I prefer a little more. Initially, it might be a little bit difficult, but at the end, it becomes a lot easier to use that method. So our first step is to write the symbols of the ions side by side. The metal should be written down first, so Mg. And you have to put the charge. So you have to go look in the periodic table, see that Mg is in group 2. Because it's in group 2, you know it's going to lose 2 electrons. So that means that it's going to have a charge of +2. And then you write the nonmetal on the right side, like this. You take a look at the periodic table, you see it's in group 17. It has 7 valence electrons. It's going to gain 1 because it's easier to gain 1 than to lose 7. Since it's gaining 1 electron, it's going to have a charge of -1. Now, usually you don't put the numbers for the 1, but I'm going to put it in this case just to illustrate what's happening. So our second step is to do the crisscross method. You circle the charges. And what you're going to do is you're going to take the charge from the magnesium, bring it down to the bottom corner of chlorine, and you're going to take the charge from the chloride and bring it down to the bottom corner of magnesium. So you're going to have something that looks like this. Mg -1 Cl +2. Now you're going to get rid of the charges, the symbol for the charges, so the minus and plus, get rid of it. So Mg1 Cl2, and then you're going to get rid of the 1. You don't need to have the 1 there because it's implied. So our final answer will look something like this. Mg Cl2. So once you become really good, you might only really need 1 step. You might have to just write the first step down initially, and then you'll be able to do the crisscross in your head. And so our final answer is MgCl2. So there's 1 magnesium ion for every 2 chloride ions that are present in the compound. On the next slide, I'm going to show you a different method that you can use called the charge balancing method. I want you to learn how to use both because the charge balancing method will become a very important tool in future lessons. So what you need to understand is that in any compound, the overall charge needs to be 0. So I'm going to start off by writing the magnesium ion, because it's magnesium chloride, with a +2. And then I'm going to put the chloride ion. minus 1. So you look at the overall charge if these two are side by side, plus 2 and minus 1. If you do plus 2 minus 1, that's plus 1. Your goal is for the compound to have an overall charge of 0. So you need to think about what you need to do to get the overall charge of 0, and a simple solution would simply be to add another chloride, Cl minus 1. When you think about it, you have 2 minus 1 charges. That's minus 2 now. So now your plus 2 is canceled out by the 2 minus 1s there to give you 0. Now what you're going to do is you're going to write down your formula based on the number of ions you drew here. So I have 1 magnesium, so I simply put Mg. I don't have to put Mg1, just Mg. And then for Cl, I have 2 of them. So I put 2 down there. This is a more realistic way to look at the compound. It really enhances your understanding of how ionic compounds will form, which you're going to see in future lessons. So your goal, again, in the charge balancing method is to make your compound have an overall charge of 0. And so you just need to do a little bit of a balancing act to figure out how many of each ion you need for it to be 0 overall. So as you can see, your crisscross method and your charge balancing method result in the same answer anyways. You can actually use both methods just to verify that you did the correct steps. Let's try another example here. So first we're going to try with the crisscross method. This is aluminum nitride. And in this example, we're going to have an additional step. It's called the reduction step. So again, we're going to start with our first step, which is writing the name of the metal first. Aluminum is in group 13. It loses 3 valence electrons. So it's going to be Al3+. Nitride, nitrogen, nitride ion is in group 15. It has 5 valence electrons. It's going to gain 3, so minus 3. We're going to do our crisscross. Bring the 3+ down to the nitrogen side. Oops, bring the 3- down to the aluminum side. And the end result will be Al 3 N 3. And here's my charges. I remove the charges to tidy up, remove the symbols for the charges, sorry, the minus and the plus. So Al 3 N 3. Now our final step is to reduce. You want to get the simplest ratio between the ions here. So what you do here, for example, is I can divide this by 3 and this by 3. And so my final answer is going to look something like this. Al 1 N 1. So 3 divided by 3 is 1. 3 divided by 3 here is 1. And you can clean up your final answer by just removing the 1s. Al N, just like that. You cannot have a fraction or a decimal as a subscript. It has to be a whole number. So if there's ever a case where you end up with a fraction, you divide it by the wrong number. We'll take a look at another example of reduction. I'm just going to do it on this slide here. I'm going to look at titanium oxide. So this particular titanium has a charge of +4. And you know that oxygen has a charge of -2. So you do the crisscross. And you get Ti -2 O +4. Tidy up by removing those charge symbols. Ti 2 O 4. but you're not completely done yet. You can still reduce. You can divide by 2. Don't divide by 4, because if you divide by 4, 2 divided by 4 is 0.5, and that's a fraction, so you won't do that. So you can divide by 2, and when you clean up, it looks something like this. Ti, 1, but I'm not going to write the 1 down because it's implied. O, 2. So for ionic compounds, it's essential that you reduce if it's possible to reduce. Now, this is where you're going to see it's actually easier to use the charge balancing method. We're going to do the aluminum nitride example with charge balancing. So, first step, write down the symbols of the ions. Aluminum becomes +3. Nitrogen becomes nitride, which is -3. Remember, in the charge balancing method, your goal is to have an overall charge 0. As you can see here, with 1 aluminum, I have +3, and 1 nitrogen, I have -3. My charge is already 0. It's balanced. So I just need 1 aluminum and 1 nitrogen, just like that. I just want you to notice that you're never going to have the charges in your final answer. You might have subscripts of small numbers if they're not 1, but you're not going to have the charges in your final answer. So here, the charge balancing method was easier. If we did the same example with the titanium oxide, so that's +4, O -2. Right now we can tell that the overall charge is not 0. It's +4 -2, which is 2. So what do you need to do to make it 0? Well, if you add another titanium, that wouldn't work. That would just give you +8 -2. That's 6. Let's try adding another oxygen. So if you add another oxygen ion, or oxide, now you can see the overall charge is 0. +4 -2 -2, and that's 0. So to do this, we needed 1 titanium, so Ti. I'm not going to put the 1 next to it because it's implied. And 2 oxides, so O2, to show that there's 2 oxides. So in a case like this, where you need to reduce, charge balancing is a little bit easier to do than the crisscross method. Again, both give you the same answer in the end, so it's a good idea to know how to do both in order to verify your answers. Let's do one more example together. We're going to do barium iodide. So I'm going to do this one a little bit quicker, skipping some steps. Barium has a charge of +2. It's in the second group. It's going to lose 2 valence electrons. Iodide is in group 17. It's going to gain 1, so -1. If you're doing the crisscross method, we're going to get Ba1, I2, and notice that I've already dropped the symbols for the charges. I'm skipping some steps here. And then I'm just going to get rid of that 1 because it's implied. You just want to make it nice and clean. Ba2. Just like that. So let's try the example of barium iodide using the charge balancing method. So in this case here, we have barium, which is in group 2. So it is going to be +2 because it's losing 2 valence electrons. And iodine, which is in group 17, so it's going to gain 1 because it has 7 valence electrons, so it's called iodide now. And so we can see that right now we're not at 0 in the charge balancing method. We're only at +1 because +2 - 1 is +1. So we need to add another iodide, and now we'll be at 0. So basically what you can do is you can kind of tally up both sides. You can look at your metal ions. You have +2 overall, and you can look at your non-metal. You have -2 overall, and so that is going to be 0. So to do this, you needed 1 barium and 2 iodides. Some of them are a little bit trickier. So for example, if you had to do the compound formed between aluminum and oxygen or oxide, what you would have to do is, we'll do our crisscross first just to show you a comparison. We have aluminum plus 3, oxygen minus 2, circle to crisscross, and then we get Al2 O3. This was our first example that we started with when I was explaining what the formula of a binary ionic compound looks like. So let's try this using the charge balancing method. We have Al plus 2, or plus 3, sorry, and O minus 2. Right now we can tell that we're not at 0. We're really at plus 3 minus 2, which is plus 1. Let's try to add another oxygen. Again, we're not at 0. We have plus 3 minus 2, which is minus 1. That's not good. Let's try to bring it back up a little bit because we want to go up towards 0 now. Let's try to add an aluminum here. We have Al plus 3 here. So now we have plus 6 minus 2, which is plus 2. Okay, now we're too far above 0. So we want to bring it back down. So we'll add another oxygen over here. And so now let's take a look. If we tally up our metals, we have plus 6. If we tally up our nonmetals, we have minus 6. Minus 2, minus 2, minus 2. That's minus 6. And so plus 6 and minus 6 cancel each other out perfectly. So now we're at 0. And to do this, we needed to have Al. We had 2 of them. And for the oxides, we had 3 of them. So sometimes it's a bit more puzzling. An easy way to have done this would have been to find the common multiple, the least common multiple between the two, between plus 3 or between 3 and 2. And so something that's a multiple of both 3 and 2, there's many things you can think of. For example, you could have 12 is a multiple of 3, and it's also a multiple of 2. 6 is a multiple of 3 and also a multiple of 2. But the purpose here is to find the least common multiple so you can get that simplest ratio over here, because remember, you'd have to reduce otherwise. So the least common multiple, sometimes you'll see it spelled as LCM, the least common multiple between 2 and 3, is 6. 6 is a multiple of 3. You can divide 6 by 3 and you get 2. You can divide 6 by 2 and you get 3. Again, 12 is a multiple, but we draw too much here and we wouldn't get the simplest answer if we chose 12. So that's why you want to choose the least common multiple between the two. That's just a quick way to do it if it's not a simple fix like it was in the barium iodide case. The barium iodide case was simply adding another iodide. There's no point in looking for the least common multiple. But in this case here, where you might have to draw a bit more. So over here you have a variety of practice problems to attempt. I'd like you to try them using the crisscross method and the charge balancing method. Some periodic tables will tell you the charge of the elements that you are working with. Others won't, so you have to know how to use the rule with the valence electrons and group numbers to figure out that charge. So just make sure you pay close attention to that. The more practice you do with these naming compounds and writing formulas for compounds, the better you're going to get. So you should get on that task immediately.